Welcome to Wireless LAN Weekly, a podcast focused on the wireless networking professional. We aim to educate, inform, entertain, and inspire. Get ready to listen and enjoy. Now to our host of the show, Keith Parsons.
Hello again, this is Keith Parsons, today with episode 7 of Wireless LAN Weekly. We're glad you could join us here today. Today's episode is a special technical-only episode. We have 2 segments, both of which are brought to us by Devin Akin. Devin's going to be talking to us about QoS, quality of service, and specifically about quality of service in wireless LAN environments. And so this is a kind of a detailed topic, and so it's going to take both sections. Of course, we'll be breaking it up with a little bit of interesting pieces and elevator speeches, etc. But on with the show with Devin Akin and quality of service.
Today's wireless networking definition from the CWNP Dictionary of Wireless Terms and Acronyms.
This is Joel Barrett, and today's term is antenna gain. The gain of an antenna is a measure of the antenna's ability to direct or focus radio energy over a region of space. High-gain antennas have a more focused radiation pattern in a specific direction than low-gain antennas. So this is Joel Barrett for the CWNP Dictionary, and tune in again for the CWNP Dictionary Term of the Day.
Rant, pet peeve, what really bugs you? 60 seconds of complaining starts now.
Hi, Elaine Rogers here from CFIN Coaching with my rant of the day. Forwarding emails and leaving in the 20 email addresses and FWs. That's a major peeve for me. I think it's a blatant sign of disrespect that you don't care that the receiver has to filter out all that noise just to read the main content. It'd be so easy to just delete all that extra content from the body and those little FWs from the subject line. I really feel that cleaning up the email shows consideration for the receiver. Sort of related to this is the fact that some of those emails are jokes or chain mails, or specifically chain emails. People seem to enjoy forwarding jokes and chain emails at will. But that means then that their address and company details, they're being sent out to 10, up to 10,000 people. It's a form of spamming, in my opinion, and spamming friends is not cool. Especially when there's a threat that their arm is going to fall off if they don't send this on to 25 people in the next 10 seconds. So there you have it, my rant for the day. This is Elaine Rogers from CFIN Coaching signing off.
Things every wireless LAN professional needs to know. Gear up, buckle down, and stand by for the real techie stuff.
Hello again, this is Keith Parsons, and today's technical topic is with Devin Akin, also known by his friends as the Devinator. And I've got Devin with me here today. The topic for the day is end-to-end QoS, or no QoS at all. Devin, thanks for joining us today.
Hey, thanks, Keith. Nice to be here.
Well, you picked a pretty tough topic here to start with. Let's get into it.
All right, sure. So the topic is about QoS end-to-end and trying to take into consideration Wi-Fi QoS as a part of that. You can't just look at it from a one-dimensional Wi-Fi QoS when the Wi-Fi network has to hook into an Ethernet network, which runs the Internet Protocol, or IP, usually. And so there's a lot of pieces to this puzzle that I want to talk about. Before I get into the layer 2, layer 3 discussion, I'd like to also say that QoS is a very large topic and perhaps the most complicated topic in the entire Wi-Fi arena. The reason for that is because there's so many things that affect the quality of service that can be delivered for applications in a Wi-Fi network. You have things like airtime fairness, which is having each type of client use the appropriate amount of airtime. You have to consider channel planning and airtime the utilization on each channel. You have to look at how does a layer 2 disruption affect upper layers like TCP. Does layer 2 retransmission affect layer 4 windowing for TCP? And what does that do to your throughput and latency? You have to consider the architecture that you're deploying. You have to think, is there a controller in the mix or not? Are we using trunks or distributed or centralized forwarding? There's a lot of pieces that go into the QoS puzzle. Today, we're only going to talk about a very small piece of this puzzle, how the layer 2, layer 3 QoS markings work uplink and downlink. So I want to jump right into that. Before we get into the guts of it, I want to give a little bit of terminology. When I say layer 2, I'm talking about the data link layer, and specifically the MAC sublayer. This has to do with Ethernet frames or 802.11 frames. Layer 3 is your IP layer. We talk about packets. Sometimes packets is used as a generic term to say any message that's happening, going in any direction. But package is more specifically a layer 3 term to describe, IP messaging. 802.11e is a reference to the amendment to the 802.11 standard. It's introduced a layer 2 quality of service mechanism. WMM is a term that's coined and owned by the Wi-Fi Alliance, which is an implementation of 802.11e QoS. 802.1p is an old school QoS term that indicates .1q or 802.1q priority markings in an Ethernet header. So most people refer to these layer 2 Ethernet header markings as .1p markings or 802.1p. And when you're using 802.1p, you're using something called frame header expansion. You have a larger Ethernet header that has 2 octets or 2 bytes extra, and those 2 bytes are divided up into 4 bits for priority and 12 bits for VLAN ID. You've probably seen that when you use something like a trunk pipe, that you have to configure the Ethernet port for a trunk or the access port for a trunk. What the reason you're doing that versus an access connection is the frame header expansion. So a trunk has the frame header expansion, the access connection does not. And so with a trunk, you have the availability to have VLAN tags and priority bits, and with an access connection, you do not. And then the next one is DSCP. That's Differentiated Services Code Point. Sometimes people call that DiffServ. That's a pretty common term. It's easy to say, and it kind of stuck when people were talking about that. But today's terminology is more specifically the markings themselves at layer 3. This is the IP header. The QoS markings, we call it DSCP. Used to be called also the TOS bits or type of service bits. So that's some terminology that we use in the QoS arena that you'll probably hear me say as we progress.
Devin, just to kick in here, just a reminder to everyone who's listening to the podcast, these terms are also included in the show notes as well as some of the graphics you'll be referring to in the future. So continue on.
Okay. Thank you. So the first thing I want to talk about is quality of service. When you have a controller and thin access points, or sometimes you hear them called controller-based access points. So QoS, when you're moving data upstream from the wireless LAN to the LAN itself. So I want to kind of do a very quick walkthrough as a client moves data to a server in a controller-based scenario. And the reason we want to talk about controllers first is that they're very prevalent in today's market. I mean, controllers, have the lion's share of the market today. And so, it's certainly relevant to talk about how things work there. With Aerohive's architecture, it's controllerless, so ours works a little differently. But in the interest of staying a bit neutral here, just explaining how it works, I wanted to give both scenarios. So first, we'll start with the client that is WMM capable, moving data to the access point. So when a client is WMM capable, the application sets UPs or user priorities, and those bits then filter down into layer 2, where they set priority values. The UPs are then mapped into the 802.11e compliant header or WMM compliant header, and then the frames are marked, and then they're put into the proper access categories. So when they go across the medium, then of course the thin access point is going to receive that and understand what those priorities are. It looks at the 802.11 header and determines, okay, this is a certain priority, and it then has to mark or take those markings, and it has to mark the information that's going upstream. Now, a thing to pay attention to here is that with a thin access point, there's an access connection. The access connection has no layer 2 or Ethernet marking ability. There's no frame header expansion, no priority bits. So we have to take the 802.11e information and move that up into the IP layer. So what you've got here in a thin AP scenario is where the entire 802.11 frame is taken and wrapped into a tunneling protocol. And so that tunneling protocol is proprietary based on the vendor. And so the whole thing is put into this tunnel wrapper, and then that has an IP header put on it. That IP header has markings that are based on and tied to the 802.11e markings that came across in the 802.11 frame. And then, of course, it has an Ethernet frame header put on there, and then it's moved upstream. It's important to note that there are no layer 2 markings happening there because there's no frame header expansion. So it's only at the layer 3 that we have QoS markings now. At an upstream layer 2 access switch, most layer 2 access switches, even if they're intelligent switches, even if they're fully managed switches, they're not going to have any layer 3 awareness. There are exceptions to this rule, but they are rare. And so the layer 2 access switch is not going to read the IP header. It is therefore not going to get any QoS information off that IP header. And there are no layer 2 Ethernet QoS markings. So it's not going to know how to handle this upstream frame as far as QoS, prioritization, queuing, or anything else at all. But it does have to mark or it does have a place to mark that information on its uplink pipe, which is a trunk pipe.
Okay, Devin, so just to recap here for a minute, the wireless client does his little marks with the WMM client and sets those codes. That's the 802.11 header, though. It hits the AP. The AP puts it into a tunnel. And on that tunnel, there is no layer 2 marking, so it uses an IP, hits the access layer switch, and that switch doesn't have any markings. Is that what you're saying?
It is. So we've translated the WMM or 802.11e markings up to an IP layer. So we've got the entire 802.11 frame that's wrapped in a tunnel wrapper, which has an IP header added to it after the fact. That IP header is, in fact, marked in most cases. And so, and then an Ethernet header is put onto that. And that Ethernet header has no frame header expansion. So when the Ethernet frame arrives at the layer 2 switch, there's no way to prioritize. It can't read the IP layer information, and there is no layer 2 information because there's no frame header expansion. So he's at a loss as to how to queue, how to prioritize, and how to mark on the uplink from there.
But he does have a VLAN trunk that's going back to the next layer back.
He does. He has a trunk that, and he's going to carry that same IP packet payload. But in order to mark the frame at layer 2, going out of that trunk to the core switch, he needs some information in order to do that marking. So how do you do that marking when you're being fed no information at layer 2 and you can't read the layer 3 information? So it goes unmarked upstream. It's not prioritized as it goes through the layer 2 switch, and it's unmarked as it goes up to the layer 3 core switch.
Well, then what does the layer 3 core switch do with it, since it can read that IP layer information?
That's a great question. So the layer 3 core switch then gets the trunked frame. It's an Ethernet frame that has frame header expansion. It then takes that off. Since it's a layer 3 device, consider it to be like a router. It's going to take that off, and it's going to read the layer 3 information. Now it has the tunneled IP packet. It reads the layer 3 information and can prioritize. So it can take that layer 3 information and use it to mark as it goes through the switch. It can be used to prioritize the traffic flow as well as to mark it on the next link, which is the link to the controller. So the important part of this is that there is no QoS handling uplink from a thin AP to the core switch. So it has to pass through a device, a layer 2 switch, that has no QoS handling.
Okay, we got it that far. And then after, how does it leave the core switch to get to the controller then?
Okay, so all controllers have trunk pipes or 802.1q VLAN trunk pipes over to the layer 3 switch. So the layer 3 switch then takes the layer 3 information, the DSCP markings, and it's going to continue to keep the DSCP markings for the IP layer, but it can then map that downward into layer 2, into the MAC layer, because it's a trunk pipe that's carrying the expanded frame header, and it sends it over to the controller. So now the controller gets this Ethernet frame that has both layer 2 and layer 3 markings. That's a good thing. The controller then is going to take off the Ethernet header. It is going to then take off the IP header, and it's going to read the priority markings for both of those as it does so. It's going to then take off the tunnel wrapper, and it's going to be left with an 802.11 frame. That 802.11 frame it has a payload that's an IP packet. And that IP packet's going to be marked as well because it was marked originally by the client. Okay, the client actually marked layer 3 and layer 2 as the information went down the stack. So it's going to get that prioritized IP packet, and now its job is to send it on to the server. So now it's going to take, after removing the Ethernet header, removing the IP header, removing the tunnel wrapper, it's going to then take the IP payload and put that in a new Ethernet frame header that's expanded. It's a trunk, and send it right back out onto the same wire that it came in on, destined to the layer 3 switch. The layer 3 switch will then get that Ethernet frame. It will be prioritized at layer 2 and 3. In other words, it'll have your 802.1p markings. It'll have your DSCP markings. It's going to then look up where the server is located if it doesn't know already, and with the standard ARP process, and then it's going to forward over to the server. Now, the server is going to be generally attached via an access port. It's not generally going to be a trunk, though that is not always the case. It's usually the case. It can be a trunk to a server. I've seen that several times, but generally speaking, we're only looking at layer 3 prioritization, but that's perfectly fine because it's directly connected. As long as the layer 3 switch had the information, the QoS information at layer 2 and 3 to be able to prioritize it going through, being processed through the switch, then the server will get it as fast as it could be gotten. So that's okay. The server then takes the DSCP value at layer 3 and knows how to process it, that packet as it goes up the stack. So at this point, we've gotten all the way from the WMM capable client all the way up to the server. And we've seen that in a controller-based scenario, we do have one point where there's a break in QoS. There's no layer 2 or layer 3 markings to help us out. We have layer 3 markings, but we can't use them, and there is no layer 2. So that is it's a break in the QoS handling that we have to deal with.
Whoa. Well, thanks for going over that, but now my brain's all full. We'll definitely need to make people go look on the show notes and see the graphic that goes along with it. So what you just described was 6 hops from the WMM capable client until it actually hits the server. That's 6 minimum hops, depends on how far back your controllers are from your APs. So at least 6.
It does.
Well, it depends on if your all your switches go directly to the core. There might be another couple hops in there as well.
Yes, I made the assumption here that we have a collapsed core architecture. Most of today's networks are collapsed cores unless they're just absolutely huge. And sometimes you'll have the core distribution access model instead of just the core and access. So like you said, there could be layer 3 hops in there. But in this case, in order to keep it simple, if you want to call this simple, we just used a collapsed core where it's only core and edge is the only 2 pieces of the puzzle, not putting a layer 3 boundary right in the middle of it.
And so the issue for anyone who's trying to troubleshoot these QoS issues is depending on which one of those 6 hops that you're looking at, the QoS bits will be set either at the MAC layer, the IP layer, or both, or inside of a tunnel. Right. In this case, since we are tunneling, we have what's known as the inside IP header and the outside IP header. When the packet the frame gets to the 802.11 access point, he takes that frame, wraps it in a wrapper, puts an IP header on that, and sends it upstream. So that IP header is actually the outside IP header because inside of the 802.11 frame is another IP packet, which is carrying the actual data payload. So it's an inside and outside. And you have 2 MAC layer headers as well. You have the Ethernet, which is outside the IP, and then you have the 802.11, which is inside the IP and outside of its own IP. So we have quite a bit of extra header overhead in a controller-based scenario because of the tunneling. Okay. Well, that was pretty intense, and that's just upstream only. And then we got the downlink to go, and the downlink's going to have to walk through the same kind of things as well. Okay, let's go downlink now. All
right. So starting at the server, he's going to try to send a frame down to this WMM capable client. Since it's an access pipe, it's going to be marked with DSCP, which is your layer 3. It's going to hit that layer 3 switch.
it's then going to be, since it's got to put this data out on the wire to the controller, it can be trunked. And so he's going to take the DSCP markings and he's going to mark, he's going to leave those in place, and he's going to put it inside of a trunk pipe, which is an expanded frame header Ethernet header, and he's going to mark .1p. He's going to send that over to the controller. The controller is then going to strip off that Ethernet header, and he's going to take that packet, and he's going to put that inside of an 802.11. That's an IP payload. He's going to put that inside of an 802.11 frame. He's going to then take the 802.11 frame and wrap it in a control wrapper, and then he's going to put an IP header on it that's marked with DSCP, and then he's going to put an Ethernet header with frame header expansion that's marked with .1p, and he's going to send that right back to the controller. We call this, whether it's uplink or downlink, we call this the traffic U-turn. You have to send things into the controller, and they have to come right back out of the controller. But when they go in, they're different than when they come out. There's different amounts of headers, wrappers, and things like this that happen since there's tunnels built from the controller to the controller-based access point. So it comes out of the controller, all nice and wrapped up, marked at layer 2 and layer 3. It's going to go back to the layer 3 switch. He's going to read those values at layer 2 and 3, prioritize accordingly, and send it downstream on a trunk to the layer 2 switch. Now, the benefit on the downlink is it's marked at layer 2. The layer 3 switch marks .1p, hands it to the switch downstream, and he says, "Oh, look at that, layer 2." So he can prioritize that accordingly. So on the downlink, you get the benefit of QoS handling on the layer 2 switch. He's going to forward that onto an access pipe down to the AP, and since he can't mark .1p, he's going to leave the layer 3 marked as is. But this is okay because the switch itself handled the QoS properly. It was able to get queued up and go through the switch, in the proper priority. So there's really not a problem with it being an access pipe on the downlink, but there is on the uplink. So the AP gets this. Now the AP has to he's got to take the Ethernet frame off. He's got to take off the IP packet header. He's got to take off the wrapper. And then he's left with an 802.11 frame, and then he's going to queue that into the right access category. Those are the queues. He's going to read that information, put it in the right queue, and then it'll be sent onto the medium at the right time. So, then the client's going to get that, take off the 802.11 header, and then read and of course he's going to prioritize that based on the QoS markings that were put into the 802.11 header at the controller, and he's going to strip that off, read the DSCP, and prioritize it up the stack accordingly. And that's the fast version.
That's the fast version. And what if he's just trying to open his first session? He has to do a SYN-SYNAC ACK. There's a 6 up, 6 back for each and every packet. Yeah.
Yes. So this is this process of uplink and downlink is just at layer 2 and layer 3. We didn't discuss how it affects layer 4, for like TCP or UDP, depending on what protocol you're using, or how the RF affects this process. We just talked about the markings of layer 2 and 3. So you can see that Wi-Fi QoS and end-to-end QoS, for that matter, is a booger. So something that is a pet peeve of mine is the complexity of configuration of QoS end-to-end. I've yet to see any Wi-Fi vendor that has completely painless QoS. The only version of painless QoS is no QoS at all. So it's not easy in Wi-Fi infrastructure unless you don't have any. And then what's worse is you have to marry these layer 2 802.11 frame QoS markings with Ethernet markings for .1p, with DSCP markings for layer 3, and you've got to do it through every one of these switches. Layer 2 switches, layer 3 switches, controllers, servers, the Wi-Fi clients. Everybody's got to be marking appropriately. Everything's got to be mapped together appropriately. Sometimes you're mapping layer 2 up to layer 3. Sometimes you're mapping layer 2 to layer 2, just a different medium. The configuration for these things is absolutely overwhelming. And if you're going through lots of hops, through layer 3 switches, through routers, it can get to be where people throw their hands up and say, I'm done with this QoS. Just give me more bandwidth. If gig's not enough, I'll go spend the money on 10 gig, whatever it's going to take. so they throw bandwidth at the problem rather than trying to configure QoS because it's simply too arduous of a task to do this end to end.
And to troubleshoot it, there's every single one of those hops. You have to know exactly what you're looking at and where the bits are and how deeply they're set inside.
If you take someone who is very skilled and experienced at Wi-Fi QoS, which in and of itself is a tremendous skill set and knowledge set, and you ask them, hey, do you understand how you're going to mark all of these access categories, these UPs, for example, it's being fed down into, to mark DSCP and to mark the 802.11 access category, or mark this traffic for the access categories, and you map this to DSCP on a switch, you know what those values are and how they normally map and what the queues mean. And the answer is usually no, because it took so much effort to learn just the Wi-Fi piece of it, to learning the Ethernet piece of it, and learning the different vendors, how each vendor implements these DSCP values and these markings at layer 2 and layer 3 on the Ethernet side is already, there's a lot of books out there written on just the Ethernet side of this thing. So this is a pretty overwhelming piece. And again, the layer 2 and layer 3 markings and mappings with Wi-Fi and Ethernet and IP is just one piece. It doesn't consider the RF. It doesn't consider the application. It doesn't consider layer 4. So you can see how overwhelming it can get.
Well, we're overwhelmed here, and we're out of time for this segment. So how about if we end up this segment, and we'll turn it into a part 2 to continue on. So this is the end of the first segment of end-to-end QoS, or no QoS at all. Thank you.
Wonderful. Thank you, Keith. Appreciate the time.
Interesting facts, little-known tidbits, things you might not have known, short little bits to set your mind a-reeling.
This is Ben Miller, and my interesting factoid about Wi-Fi is when you're doing Wi-Fi sniffing, the error percentage really isn't of much use. When you are using a sniffing tool or any tool that is showing you errors, that's just showing you the errors that are being received at your sniffer. It's not really an indication of network errors, and something that took me a little while to kind of understand, but now it's something that I just find interesting.
Elevator speech. Our guests have just 2 minutes to tell us all about their product or service offering. Ready, set, go.
I'm Justin Lucas Savage at CoachRadio.tv, where I'm helping you do business better. We're here every Wednesday at 4 p.m. Eastern, and we help people connect their ideas and turn them into income and turn their passions into profit. If you have something that you're passionate about, there's no reason whatsoever you shouldn't be working in it day in and day out. So the biggest thing that you need to do right now is to figure out what it is that fires you up, that keeps you awake at night, that gets you out of bed and early, and then get about the business of doing it. What are you waiting for?
Things every wireless LAN professional needs to know. Gear up, buckle down, and stand by for the real techie stuff.
Hello again, this is Keith Parsons back with the Devinator with Devin Akin talking about QoS. We finished up on the last segment with QoS with the controller and then APs walking through both the uplink and the downlink. And again, you'll be able to check out the graphics for this in the show notes. So Devin, let's continue on here with going on to what happens if you have no end-to-end QoS.
Great. Thanks, Keith. Thanks for having me. So last time we talked about how QoS works uplink and downlink with WMM-enabled clients and how the frames and the packets move from end to end across the simple network. So now to continue on, let's take the controller scenario and finish up on that, and then we'll move into a controllerless scenario. So we've already talked about how on the uplink we have no prioritized handling through the layer 2 access switch at the edge, and that breaks your end-to-end QoS. For reasons like that, a lot of people throw bandwidth at the problem and hope that QoS is not nothing they're going to have to configure, and that doesn't always work, but it is how they solve the problem sometimes. Some other pieces of this puzzle with a controller-based scenario that you need to keep in mind, and that is that the QoS decision maker, the controller, is several milliseconds away from the AP and the client when the decisions for QoS are made microsecond by microsecond. So, it's hard for you to control airtime and to control queuing and to which queue is full, which packets are being dropped, or I should say frames are being dropped, things like this when you're that far removed in time from the point that in the network that is making those decisions or should be making those decisions, and that is the access point. So that's one thing to keep in mind. I know we're talking milliseconds and microseconds, but a millisecond is 1,000 microseconds. So you can see that even though we're talking small scale time values, they're like a lifetime to controllers and access points and clients. Another piece that filters into this is the airtime fairness mechanisms. When the controller is making decisions about airtime fairness rather than the access point making those decisions itself, you don't have the granularity to really do much control, much airtime fairness mechanisms. In other words, it just simply won't work very well. This is important because this is what I call, it's a slang term, but I call it layer 1 QoS. I've been saying this since my days at CWMP. I first saw this airtime fairness feature with Maru's platform, and it's pretty impressive. And in fact, Maru does this at the access point. They have to do it at the access point if they want it to work. Even though they're a controller-based architecture, they have to push this information, this functionality down into their access points to make it work. And that's something that Aerohive figured out as well. You have to do these types of functions right at the AP. Some vendors don't, so their airtime fairness mechanisms don't work that well. So that's an important piece. Regardless of how you handle the layer 2 and the layer 3, if you're not handling the layer 1 very well, it's like building a house on sand. It doesn't matter how sturdy your house, or if you're building a brick and block, this doesn't make any difference. The sand's going to shift underneath your feet, and your QoS is not worth much. So that was why a lot of vendors are trying to get the airtime fairness mechanisms to work well.
Well, Devin, if that's the case, you mentioned airtime fairness and QoS markings. I'd also like to kick in not just the airtime fairness happening at the RF layer, but all other RF layer issues. If you're on a single channel, that frequency has a capacity to carry information, and it really doesn't matter what QoS bit you set on the uplink, you're sharing that time with everyone else. So between the airtime fairness, RF arbitration, and then trying to get the QoS to work, how does all those three things kind of tie together?
Well, they certainly do tie together, and that's a wonderful question. Airtime fairness, we have a mechanism at Aerohive called dynamic airtime scheduling. And as I'm sure you're aware, that's just a marketing term for how we handle and we'll see a little bit later, how we handle this problem. We do an airtime fairness type of mechanism, but we do it with a scheduler. So we call it, and it's very dynamic. So we call it dynamic airtime scheduling. But you're right. Everything from RF interference, obstacles, clients with different physical layer specifications, or PHYs as we call them, that are fighting for airtime, some faster than others, some slower than others, some having problems communicating because of RF obstacles or interference, some at different distances. All of these RF factors play into the layer 1 handling. And since layer 1 is an underpinning to the layer 2 and layer 3, the Ethernet or 802.11 and the IP layers, you have a scenario where if the layer 1 is not handled well, the layer 2 and layer 3 just don't matter. It's the airtime management, the interference management, the high-density client management. All of these things actually matter more than the layer 2 and layer 3 QoS piece. But certainly that's not what we're trying to explain today. But you're right; they're tied together. They're very important, and the RF handling is a more important piece of the entire equation than the markings of layer 2 and layer 3.
Okay, well, good answer there. We still don't have a firm grasp on that because those are pretty complex, and that's really not what we're talking about here. So continue on with the QoS.
Thank you. So in a controller-based scenario, data has to flow through the controller in both directions. And again, we call this the data U-turn. This causes latency. When you're decapsulating and encapsulating, putting frames into tunnels and taking them back out, and putting them back onto the same wire, this U-turn causes latency. And when we're talking about priority, handling and quality of service, we want to make sure that there is the least amount of latency from end to end. That is from client to server or from client to client, or, whatever the case is. If it was, voice, it might be client to client. If it was a video stream, it could be server to client or something like this. So we want minimal latency, and having a single point where all data has to flow in and turn around and flow back out can cause latency. And it can be worse if the controller is oversubscribed. That's also a piece of that's something that's we consider, the competitive part of, in the industry. We're controllerless, so we don't have to worry about this. And I don't mean to go into that piece of it, actually. I'm not trying to make this into a competitive thing, but it's just something to keep in mind that if the number of APs and the amount of throughput that these APs can push, and if they do push that kind of throughput through a controller, you can oversubscribe the controller to the point where QoS is almost worthless. It's just so much traffic trying to get in and get out that the controller can't handle it. So you have to have more controllers, and that's certain. And for every controller, you need a redundant controller, for resiliency and things like this. So there's just some things to keep in mind. Other points are that two legs of the connection have no layer 2 QoS markings on the uplink, which is from the access point to the layer 2 switch, and from the layer 2 switch to the core. This causes a lack of prioritization and at the layer 2 switch. It breaks end-to-end QoS. And thin APs support only the WMM queuing mechanisms, which are very coarse. Do they work? They usually work okay, but when you get into some scenarios, high traffic density, high traffic flows, a big mix of high throughput with dense voice and things like this, this becomes a bit of an issue. WMM is just incapable of handling really tough situations. So the next point I wanted to get to was the end-to-end QoS without a controller, and how is it different? Most people don't even understand how a network can work without a controller, because we've been so accustomed to seeing controllers, for the last 6 or 7 years. We've seen, controller, if it's Wi-Fi, it's got a controller somewhere. And so, Aerohive's, approach to this without a controller, they're thinking, it's just an autonomous access point. Well, it's not. We do the same functions that a controller does, but we do it in software rather than in hardware. And so the end-to-end QoS works a little differently.
For the sake of this discussion on end-to-end QoS without a controller, would an autonomous AP, just from the QoS standpoint, have the same traffic flows as the Aerohive AP in the same scenario? Not talking about the controller functions, just the QoS piece.
The answer to that is yes. So the autonomous access points, generally speaking, you would see them connected to the infrastructure with a trunk pipe. That is, each SSID was tied to a specific VLAN ID. And so in order to have multiple SSIDs on autonomous access points, you had to have multiple VLAN tags, which means you have to have a trunk port. Okay, so there were some really good scenarios there. I mean, people, a lot of people didn't like the fact that you had to have a trunk port to the edge, but in today's Ethernet switching and access point technology, trunking is automatic. It just turns on by itself. And so there's really not a lot of extra configuration. And having trunks at the edge allowed for fully distributed data forwarding, which means you have minimal latency. It means that you have expanded frame header expansion already, so that you can do QoS at the edge, which is QoS should always be done at the edge. That's just normal, good network design. That it's always been done that way, and is prevalent everywhere. So that in autonomous access points, those were good features, good qualities, and Aerohive doesn't want to take away from that. Doesn't want to detract from the fact that autonomous access points had some good qualities. Certainly, there was some negative qualities there. The fact that they didn't trade control plane information, things like radio resource management is one. Fast, secure roaming information is another. They didn't trade this type of information back and forth between APs, and so they had some problems that caused the industry to move to controllers, and it made perfect sense to do so. Does that make sense?
That does. Thank you. So basically, from the QoS standpoint, as you're continuing on this end-to-end QoS without a controller, the QoS packets would be the same whether it would be an Aerohive or an autonomous AP.
That's correct.
Okay. Continue on.
All right. Thank you. So the movement of messaging from the WMM capable client to the to a server, let's say, just a unidirectional. Actually, you can say bidirectional. It's the same thing. Every leg of the link is marked and handled properly. If you go from the client, all the same markings, DSCP, 802.11e, it's all the same as it was in the controller scenario. You hit the access point, and Aerohive access points are typically deployed as trunks. You don't have to. You can deploy them as access ports if you want. But for optimal scenario of distributed data forwarding and things like minimal latency and frame header expansion for QoS, all these things are possible by using trunks at the edge. And since this is almost an automatic thing these days, there's really no extra overhead, and it leverages the speed of the Ethernet. You don't have to tunnel all the traffic back to one point in the network for single points of failures and bottlenecks. You can just utilize your fast Ethernet network there, whether it's gig or 10100 or what have you, and it's all trunks. So you're going to get the .1p markings. You're going to get the DSCP markings. They're going to hit that upstream message. Is going to hit that layer 2 access switch, and it's going to be marked with .1p. So even though it can't read DSCP, it can read the .1p, and it's going to take that information and pass it through to the other side, where it's going to stay marked on the trunk up to the layer 3 core. All the same markings will apply. And then, of course, it's going to DSCP will move over to the server, since the server is generally connected with an access pipe. That's the same as the controller scenario. So the real difference here for QoS is how the connection between the access point and the layer 2 work, as well as you don't have the latency at the controller, the bottlenecks and things like this that we have to deal with in a controller scenario. So there's really no break in end-to-end QoS, just as there wasn't with autonomous access points.
Well, you make it sound a lot simpler. Though still, from a count standpoint, it's going to be 4 hops to the server anyway. Client to AP, AP to access switch to core to server. So, right.
There's the 2 pieces you're going to remove here is the hop to the controller, the hop back out of the controller. So that's the traffic U-turn we were talking about that causes latency and bottlenecks.
And what we also added now in this model is you have the layer 2 and layer 3 markings going from every single hop, and there's no tunneling going on.
That's right. So having the trunks at the edge, again, allows for distributed data forwarding, which means the data flows directly from the source to the destination. There is no intermediary point. There's minimal latency. There's no need to buy layer 3 aware, layer 2 switches at the edge. Every hop, every segment carries layer 2 and layer 3 markings, and this gives us end-to-end QoS. They also, an old saying that I've heard for a really long time is QoS is end-to-end, or it's no QoS at all. That's why we titled this presentation that, because that's something that I found to be true pretty much across the board. So we've gone through the controller based, the the controllerless based. Some other topics that are really important in this whole layer 2, layer 3 QoS piece is moving from a fast network to a slow network. And that's all relative, of course, because, what does fast mean? What does slow mean? Well, for my purposes, just for this presentation, fast is full duplex gigabit. Let's get as a reference point. And slow is a shared 802.11an or 802.11bgn simplex environment. It's a shared medium. So without a sophisticated QoS at the edge of the network, there can be there could be a significant congestion at the AP for the downlink. And the reason for this, if you think of a 4-lane highway and it's moving into a 2-lane highway, everybody's got to converge into these 2 lanes. Well, it's not a big deal if there's not much traffic, right? Everybody just kind of weaves themselves in there. It's no big deal. Well, if you suddenly have 4 full lanes of traffic, things are moving very, very fast, and then you move into those 2 lanes, you have a mess. And so you have to have something at that point to control that, to say, okay, we don't want cars. Excuse me. Pause there. Maybe you can cut that out.
Got it.
We don't want cars to crash. We don't want cars to go off the road. We don't want cars to stop. We want to weave these cars in very tightly, like air traffic control would do. You have lots of planes. You have to pack them tightly and very carefully so we don't have any crashes. That's what an access point is doing when there's a heavy downlink flow, when you're moving from full duplex gigabit into a simplex shared network that's like a 802.11a or 802.11n or what have you. So my question then becomes, and I ask this as a rhetorical question, where do you do this control point? Do you do this at the access point where that's the interface between the 4-lane highway and the 2-lane highway on the downlink? Or do you do it miles ahead of time at the controller? When I say miles, what I'm saying is milliseconds ahead of time when we're dealing with microsecond by microsecond. It's not really possible to pack all these frames tightly, to control and interweave all of these frames way ahead of time. It's not possible. You have to do this at the edge of the network, right at the point where the mediums link together, and that's the access point. So the handling of QoS needs to be done right on the AP. Now, in defense of some controller vendors, they do this. Some controller vendors handle QoS at the thin access point. There's certainly some limitations there if they're using access pipes, as we've already discussed. But just the same, the QoS handling should always be done at the AP, and when it's not, it's a lot less effective. So along those lines, let's talk about how granular QoS the edge should be and what today's standards are. So we're used to dealing with wireless multimedia, or WMM, as our QoS mechanism. That's a term, if you're in Wi-Fi or you have been in Wi-Fi for very long, you've probably heard that term. The Wi-Fi Alliance they have a certification for WMM, and it uses access categories and UP markings and all these different things to prioritize frames at layer 2. And so Aerohive finds that this mechanism is quite coarse and has the potential in many environments to drop frames. And it is a pretty big deal to drop a frame at layer 2. It causes latency, and because of retransmissions, some applications don't like this at all. And in fact, it can affect upper layers like layer 4. If you drop frames at layer 2, it could cause layer 4 retransmissions. And when you cause layer 4 retransmissions, you change TCP window sizes oftentimes. And when you do that, you could cut your throughput down substantially. So we don't want dropped frames. That's a big no-no.
Well, the slide that goes along with this, and again, the picture of this is in the show notes, this granular QoS at the edge, as you try to add, you have those 4 categories with WMM. This is looking pretty complex, how you take and how do you granularly make those to go further down than just the 4?
That's a great question. This graphic, it looks pretty complicated on its surface here, and I won't say that it's not. Each piece of this logic lives inside of each access point. The traffic comes into an access point, and we're talking downlink now. Comes into the access point, and it has to be classified, policed, or rate limited. It has to be marked appropriately. It has to be put into queues. And in this case, we have queues, up to 8 queues. That's per user or per user profile. And so we're very granular in how we queue this traffic up. And so, certainly this requires quite a bit of memory and things like that in the access point to be able to pull this off. And then these queues are filling on a per user or profile basis. And then the scheduler comes along and he looks at that and says, okay, he's playing middleman between the queues that we have for each of the user or user categories. And then he looks at the WMM queues, which are the interface to the air, the wireless medium. And he says, well, if this traffic comes in, it goes straight into these WMM queues, these access categories. If they fill up, traffic could be dropped. So instead of letting traffic be dropped because the queues are full, instead of doing that, we're going to have these queues behind the queues. And the scheduler knows what the QoS policy is. It could be voice, and we could say this is a strict policy. All voice goes out before data, period. It could be a weighted fair queuing policy, or some hybrid. You get to in the Aerohive platform, you get to decide how you want to do your QoS. And of course, you have to understand what the QoS is all about, and things like that. There's all this terminology you need to understand for anybody's QoS. But but being able to queue behind the queues is very important so that nothing gets dropped. Everything is prioritized according to the policy, and the upper layers are unaffected, and this gives you maximum throughput. It gives you the best possible QoS scenario. We just found that WMM is just not quite enough for every scenario. It's good enough for some lightweight scenarios, and a lot of networks have a very lightweight scenario. But when the rubber meets the road, sometimes it's just not good enough. And so implementing this, it looks complex, and I guess you could call it complex. Luckily, you don't have to deal with the complexity part of it, but this lives in every access point.
Well, thanks, Devin. That was I've never looked at taking QoS past the WML level, and it looks like Aerohive's got a solution there that allows you, what did you call it? Queuing the queues.
Queues before the queues.
Queues before the queues. Pretty good. Well, great. Well, this is the end of the second part of this series. There's two parts. The first part we covered controller-based QoS, and then the second part we did the non-controller-based QoS, and then ended up here with a little bit of some Aerohive specific pieces that you do to add some more granularity into the QoS. Anything else you'd like to comment on?
I don't think so. If this isn't enough for this time, maybe I can come back and present some more on the layer 1 QoS at another show.
I see a lot of layer 1 QoS issues going on as well. So maybe we'll bring that up as on a different episode. Well, I appreciate your time, and we'll have obviously the graphics in the show notes. Is there a place that people can contact you? Where would you like them to track you down?
Sure. People can always contact me at devin@aerohive.com. Pretty easy to remember, and I don't mind the emails.
So you try to get to, inbox 0 once a month or something, get all the way down to 0?
I look at this as an opportunity to, whether it's a podcast or a voiceover PowerPoint or talking at a show or anything like that. It's an opportunity to talk to customers, partners, the audience in general, and I personally enjoy helping people. So this whole thing is a fun experience for me, and I don't mind giving out my email address.
Glad to have you. We'll drop that in the show notes as well. Well, thanks for your time today, Devin. Appreciate it.
Thanks, Keith. I appreciate you letting me participate.
Thank you. Well, we've finished up on the quality of service with Devin Akin's little bit there. Actually, long bit there. There's a lot in there. Be sure you go check the show notes out, and there's some supporting graphic that would help in this. We're glad you were able to come and listen to episode 7 of Wireless LAN Weekly, and hopefully you'll continue to send us feedback and information about what you'd like to see in the show. Thanks for listening today, and we'll see you again next week.
Wireless LAN Weekly, a podcast focused on the needs of wireless LAN professionals. We look forward to your feedback. Please leave your comments at the bottom of the show notes, or email feedback on the show can be sent to feedback@wirelesslanprofessionals.com. If you'd like to leave a voicemail feedback, just call 24/7 and leave a message at 1-801-481-9018. Until next time, this has been another production of wirelesslanprofessionals.com, a place to educate, inform, entertain, and inspire.